Hi, welcome to the QCT speech today. My name is Alex Mew. I'm the Networking Software Group Director in ASTRI. Thank you for QCT to invite me today to talk about 5G standalone core network challenges. To give you some introduction about my role and what ASTRI is doing, ASTRI is a government-funded organization in Hong Kong with objective to do R&D and commercialize our technologies through our partners into products. And my team, networking software, has been focusing on core network development since the 4G era. And also, we're also looking at smart mobility use cases as well, so that it will leverage the 5G to enable more smart mobility capabilities. Today, I'm going to focus on 5G core network because in 5G, there's a new architecture called standalone architecture that is very important for 5G to enable the applications. So when we talk about 5G standalone core network, we need to think about a few things in terms of requirements. First of all, 5G delivers a very high throughput and low latency communications in the radio network. At the same time, we also need to think about when we enable different applications, we need a lot of flexibility. For example, some applications you need a high throughput, then you need a certain configuration, and some configuration you need a low latency. Also, some traffic isolation and additional security. You will need to organize the network in a different way. So deployment flexibility will be very important, and I will go through a few use cases that we have been exploring in R&D. The second matter is the performance, because 5G, a major difference from 4G and 5G is the performance. The throughput has been significantly increased, and the latency requirement becomes more stringent. So we need a higher performance core network to deliver the needed performance. The third area is the scalability. In terms of scalability, we need to think about both in scale out. Traditionally, when we talk about scalability, we talk about scaling out to many servers in cloud scale. That is important for 5G because we need to address different applications and scale up of number of users, number of throughput, and the number of applications. But at the same time, we also have scaled down configuration requirements because you will imagine very small enterprise, they can still enjoy 5G, but their capacity requirement is much less than what a network operator will need. So we need a way to scale down the 5G core network, even into a single machine that allows a very simple deployment. The third area is we call API or application-driven mindset because unlike the previous generation of 4G, the core network is pretty much static in terms of the application. When we deal with the 5G core network, we also need to think about what application that it is going to power so that it can do additional APIs that's suitable for that kind of application scenario. So cost effectiveness being a very important area. The ability to use this general purpose system not only allows you to have a cost effectiveness, but also have a very high a very short time to make a deployment. The last area is the manageability, which is very important because 5G enables what we call edge computing that requires many core network components being deployed either remotely or in an edge location. That makes the manageability very important for 5G. So how we are going to make it more easy to manage will be another factor that we need to consider. So first of all, we talk about deployment scenario. So we kind of use different topology to explain the different situations. The first one is private network on premise. This is the most simplest method for private network deployment because you can have the whole core network being deployed only serving the enterprise, which is installed on premise. So, and everything is LAN connected. You don't need a wide area connection. You just need to hook up the base station in a LAN and then power up the private network. Also, you will notice we separate the control plane and data plane here, which would have more explanation later on. The second area is network slicing. I think when we talk about 5G, these terms often comes along. We call horizontal slicing because you will imagine the network elements, the whole network, the control plane and data plane can have different slices working on the same platform. So typically, this is a network operator, mobile operator. When they deploy network slicing, they will have the whole network sliced in different applications. And we also have MVNO, mobile virtual operator. They are a bit different because their services, they only need to provide a certain number of network elements for 5G core, while most of the RAN and most of the control plane elements are provided by the host operator. So in this situation, you will imagine that MVNO could have their system deployed outside of the host operator, and perhaps they would need a different way because first of all they need to consider how it's going to support the edge computing scenario. The second of all, the traffic demands actually would need to scale, and the way that we see that using a cloud-based deployment in the public cloud or in the private cloud would certainly serve the purpose, because for mobile virtual operator, the number of users may scale differently, and they may have different operator to collaborate in terms of hosting. So we're also exploring mobile operator scenario. The fourth area is also focused on network operator. We see that the terms called CUPS, control user plane separation. That what it means is the control plane is sitting on a central location in the mobile operator, maybe a central office or even more a hub site or whatever. But the issue about 5G is the scale up of number of users versus the throughput may not match symmetrically. So when we deploy the cases, we do need to figure out how we use the edge computing or edge node to scale out the network to support more bandwidth. At the same time, we can easily imagine there are low latency applications that requires the UPF being deployed near to edge so that those applications can be supported. And then the enterprises can be more interesting. The first scenario I explained was about private network. However, in a enterprise, you can also have network edge because in this scenario, you can imagine that a multinational or multi-site user enterprise, they can have multiple factories, they can have multiple offices. What they need to do, they only need to put the data plane on premise so that the data can maintain the isolation without going through the internet or some untrusted network. Also, without going through the WAN, the throughput and latency, the quality of those can be maintained within the premise. But of course, in this scenario, we could imagine applications that requires connection between sites can also be enabled. You can see the data plane sitting in the middle, sitting on the right-hand side, is on a central location. What it does is it allows the edge node, the edge UPF, to forward the data through the cloud to the central UPF, and it acts as a routing to another site. So you can imagine the first site here can forward the data to the second site. And the beauty of this scenario, not only the data offloading, but also the management. Because normally for the control plane, it is very relatively complex to maintain and manage because they need to maintain the states. And by having the control plane sitting in a central location, it allows the central administration to take place more easily, while the data plane is more simple to be managed by the local site administrator. And for the sixth scenario, it is even more complex. Even within the same site, you may have different applications. And different applications, they have different QoS requirements, or even different topology. For example, some video surveillance would have much more high bandwidth on the uplink, and some manufacturing teaching applications you will have low latency but relatively low bandwidth. And in terms of application, you may want to segregate them into different virtual network, VLANs, for example. So and apply different QoS on it. So by doing so, you can have a much more flexible core network for the enterprise to serve different applications. But at the same time, if you see the right-hand side, you still have the control plane being centralized. But you also see that on the lower right-hand corner, there is a public cloud service. Because nowadays, many of the data, after it is being processed locally, it would still ship to the enterprise applications, like for example, maybe ELP or some kind of centralized application to manage the inventory and so on. That is hosted on the cloud. So this architecture not only allows data to be consumed locally, but also it taps into the public cloud service. In that situation, you will need something similar to SD-WAN to support that kind of deployment, so that different sites can use a software-defined way to connect to the public cloud, so that the data can be fed into the public cloud service hosted by the enterprise. So there are many new possibilities and many new capabilities that we need to address. But the sixth scenario that I list is not it's not the limited list. There are still many different scenarios that we're going to try. But out of all that, what else do we need? We need some key capabilities in the core network to support those different deployment scenarios, performance, and a few other parameters that I mentioned. So first of all, on the UPF, you need to support a network instance. What a network instance is, it is a logical network that allows you to tap into different network. And when we talk about different network, they will have different IP address range. So by having a virtualized IP address range, it allows more applications to be deployed. Imagine that you can deploy many applications, but and many users using it. However, your IP address space would consume it very rapidly. But using network instance, you separate the applications onto different network instance, which has its own IP address pool. Then you will have much better scalability and better manageability on the network. And it also allows you to connect in the backend. After the data is connected from the 5G, it allows you to forward the data to, for example, internet, a VLAN, or through a VPN tunnel to another site. So the case that I mentioned in sixth scenario previously would utilize this. You have a tunnel that goes to the cloud, but also a VLAN goes to a different application. The second capability is the edge capability. So in 5G specification, a few key parameters are needed. The first one we call N9 interface. The N9 interface is the interface between two UPF. As you can see in this slide, the edge UPF is located in the edge location, and there are centralized location. The link between them is called N9. And what it gives is a uplink classification capability we call ULCL. When the packets come from the radio network, it first arrives at the local edge UPF, and then the uplink classifier will determine what packets needs to be offloaded locally. And this kind of path management and the filter rules are managed by the PCF and also local configuration. But the to enable this situation, you also need a PCF API that allows the application to provide the application data, for example, the filtering rules and the QoS requirements into the 5G network, so that it will eventually arrive to the UPF to do the required handling. Lightweight and virtualization is also very important. Lightweight meaning that you can consume very few resources in terms of CPU, memory, and so on. It also means that you can capture it using a VM or even containers. And now our core network do support containers for all the control plane and data plane network elements, network functions. So using containers, you can imagine when we add network slicing or adding additional applications, we can use container to scale out the applications. And using virtualization, we organize your network topology more easily. And manageability. You will need a architecture that allows the what we call zero-touch management capability, usually being referred in the SD-WAN technologies. But the beauty of zero-touch capability is to allow for example, a user plane that being deployed on a remote area, they don't need local site management. After it powers on, it automatically talks to the centralized controller and orchestrator to obtain the configuration. And all the administration capabilities are provided in the cloud. So locally, they may just only need to hook up the Ethernet connections per requirement, and then that's it. All the configuration, all the management are done in the cloud in a centralized way. That reduces the overhead for local users. And also, we also experienced previously when we deploy private network, those companies, those enterprises may not have enough experience in terms of managing a 5G or 4G network. That would become quite complex to them. But in this model, zero-touch capability will allow the more experienced people to essentially manage, either by a centralized administration team or hosted by a network operator or some sort of service provider. This makes the 5G more easily to manage and more easily to deploy in enterprises. Last but not least, we're working very hard to increase the performance, working with QCT and Intel, and some R&D is focusing on increasing the throughput of 5G core network. So we are able to achieve very high throughput. In past year, in 2019, we successfully demonstrate 200 gigabits per second purely software on a single server using the off-the-shelf hardware, and the implementation is purely software-based. And this year, the performance even increases more. So this requires a close collaboration with the platform provider to have a optimized solution and also do performance validation against the target application and deployment scenario. And I would also like to talk more about our collaboration with QCT. As I said, we have been developing the 5G core network. We now have a few major network elements being mature, and also the completed interoperability testing with some base station vendors. And that includes AMF, SMF, AUSF, UDM, PCF, and so on. And also UPF. Some of the elements we're going to develop throughout 2020. And in this configuration, you see that we are also optimizing the performance on the platform, so that we can have scale out of data plane on a server and control plane on a separate server. So the performance that we can achieve is quite high. On a per slice configuration, we can achieve 16 gigabits throughput uplink and downlink. That consumes about 4 CPU cores in the system. So you can imagine this configuration allows you to scale out the UPF more easily. So I wish to conclude my presentation today. And if you have any questions, you can certainly contact QCT or contact me through the email address shown on the screen. I really appreciate your time today, and I look forward to hearing from you and learn more about 5G core network if you're interested. Thank you very much. Bye-bye.